right, so I think we can start. We are now having the closing talk of the week by Andreas Ringwald from DESY, who's going to talk to us about a new exciting way of exploring the early history of the universe with gravitational waves.
So thank you very much for the nice introduction and for the ability to be here and to have the first now in presence workshop. Now this work, so I'm reporting here on work together with Carlos Tamarit from the Technical University in Munich, from Kenichi Saikawa, who was previously a postdoc at DESY, and from Jan Schütte-Engel, who was my PhD student, but he's now in US and enjoying the postdoc there. So, as we all know, so the Big Bang cosmology describes how the universe expanded from an initial state of extremely high density to the cosmos we currently inhabit. And it comprehensively explains a broad range of observed phenomena, including the abundance of light elements, the cosmic background radiation, and the large-scale structure. So, but somehow we don't have direct access so far, or direct information so far from the cosmic history prior to Big Bang nucleosynthesis. And as several speakers have already emphasized in this week, of course, the stochastic gravitational waves produced in the early universe, they may be a unique and direct probe of the cosmic history prior to Big Bang nucleosynthesis. Now, an eventual measurement of the complete spectrum of the stochastic gravitational wave over the whole frequency over the whole frequency range may inform us, in particular, about three cosmological events which many of us think or are supposed to have been occurring in the very early universe, namely, first of all, a stage of inflationary expansion preceding the radiation-dominated era, and we had several talks about that in the conference. The next is the subsequent reheating stage, and finally the beginning of the hot thermal radiation-dominated era after reheating. And in my talk, in these stages, gravitational waves are produced through quantum fluctuations during inflation. So, as I said, we had many talks about that. In the post-inflationary stage, we have gravitational waves are produced through inflaton fragmentation, and finally, in the beginning of the hot universe, there are vital particle collision, and so they produce also gravitational waves. And I'm reporting here on the determination of the complete spectrum of stochastic gravitational waves from a well-motivated and very predictive minimal expansion of the standard model, which predicts also the cosmological history from inflation to today. Now, what model is it? So some people think, of course, they immediately know what I will be talking about. So it's the SMASH model, the standard model, axion, seesaw, Higgs portal inflation model. It's a minimal model of particle physics and cosmology, and this we developed together with three Spanish colleagues. So one, Guillermo Palesteros, he was also here this week, and the last week, but he had to leave already, Javi Redondo and Carlos Tamarit. So SMASH extends the standard model by three right-handed singlet neutrinos, a standard model signet, complex scalar sigma, which we can think of as a real part and an imaginary part, and a vector-like extra quark Q. So this is the minimal added field content to the standard model. And it is supposed that they are all charged under a new global U1 pitching wind symmetry that is spontaneously broken by the WEF of this complex scalar, and the WEF should be around 10 to the 11 GeV. Now, this model solves 5 big problems in particle physics and cosmology in one smash, and therefore it's called smash. So, let me start here. So first of all, here in this sector, this solves the strong CP problem by the Petschek-Wien mechanism, and it solves the dark matter because this so the pseudo-Goldstone boson associated with the symmetry breaking of this Petschek-Wien symmetry is a dark matter candidate. In particular, if this symmetry breaking scale is around 10 to the 11 GeV. Moreover, then of course these neutrinos masses and mixings can be explained by the type 1 seesaw mechanism, by these neutrinos which get because they were charged under this global U1 Petschek-Wien symmetry, and of course they had the appropriate Yukawa couplings. These heavy neutrinos, so they have this high masses, and therefore may explain the masses of the active neutrinos by the type 1 seesaw mechanism. And of course, you have these high masses are also good for thermal leptogenesis to produce the baryon asymmetry. Now, this model we had already proposed before, but then when I met Guillermo in Hamburg, he was there as a long-term visitor. Then he talked about Higgs inflation, and then I told him, look, I think in this model we have of course also the inflaton candidate, but we can do it with a mixture between the Higgs the Petschek-Wien scalar and the Higgs field, and avoid many problems which one has with normal Higgs inflation. Now, so let us start with that. So I'm starting now with the gravitational waves from quantum fluctuation during inflation, which are predicted in this model. So what we will use is the Higgs portal inflation, and so we have shown in these papers that the mixture of the modulus of the Petschek-Wien field with the modulus of the Higgs field is a viable Higgs inflaton candidate. One has to take into account or exploit the unavoidable non-minimal coupling of the Higgs and the Petschek-Wien field to gravity. In particular here, now we are assuming that the psi sigma, the non-minimal coupling to the Petschek-Wien field is much larger than to the Higgs field in order to get inflation along the rho direction rather along the Higgs direction in order to avoid problems with perturbative unitarity. Now, this is well known, these non-minimal couplings stretch the scalar potential in the Einstein frames and make it convex and asymptotically flat at large field values. So this comes just from this conformal from this conformal factor. If you go now to large field values, then essentially the quartic coupling, only the quartic couplings survive at very large field things, and so if this term dominates, then to leading order, the fields themselves cancel out. Now, so as I said, we require that this psi sigma is much larger than this the minimal coupling to the Higgs to avoid problems with perturbative unitarity, and we also require that this psi sigma should not be large, just in order to avoid these perturbative problems with which Higgs inflation must face. Now, for negative portal coupling, if this lambda h sigma, this Higgs portal coupling is less than 0, the scalar potential in the Einstein frame has a valley or attractor for inflation along this line, and this so inflation in this direction has turned out. And in this paper we made a very general analysis, and we found that in this direction reheating, a larger reheating temperature is produced, and one avoids problems with dark radiation of axions. So we'll exploit this direction, and then of course one ends up with an effectively single field inflation with a potential now which is very flat outside, and then when rho becomes of the order of the Planck scale, it gets steep. Now with this kind of potential, one can now do all this the inflationary gymnastics. So slow roll inflation along this potential produces scalar and tensor spectra which are consistent with the CMB data. So everything inside this blue line is consistent with the CMB data. If this psi sigma is larger than 7.10 to the -3, which is the lower bound, comes from the upper bound on the tensor to scalar ratio. And so, as I said, we require that we do not want to get in this region. So this lambda tilde sigma should be smallish, 10 to the minus, between 10 to the -10 and 10 to the -13. And there is the tensor to scalar ratio in this single field model is bounded from below, and it's bounded from below to such a degree that it's observable at the next generation of CMB polarization experiments. So here is our prediction. So this is the prediction taking into account that in this model we can calculate also the number of e-faults very precisely. So the prediction of inflation in SMASH lies along this black line, and this is so to say the sensitivity of for example, forecasted sensitivity of CMB S4. So this model can already be falsified in the next generation of CMB polarization experiments. However, we have then looked more deeply in the predicted spectrum, the whole spectrum of gravitational wave from inflationary fluctuations in this paper. So as of course, this spectrum can be written as split in two factors. One is the power spectrum of gravitational waves during inflation, expressed in terms of the present day frequency. And here I have used here so inserted as benchmark the values of the Hubble expansion rate during inflation, which is obtained from the fit to the CMB data, which is of the order between 10 to the 13 and 10 to the 14 GeV. Then, of course, then there is this other factor, the transfer function, which accounts for the evolution of the gravitational waves after their modes re-enter the horizon after inflation. In this case, of course, this transfer function is sensitive to the equation of state of the post-inflationary universe at horizon crossing. So this equation of state functions or effective degrees of freedom enter into this way in this equation of state, and where this horizon crossing temperature as a function of f is the temperature at which the mode corresponding to the frequency f re-enters the horizon after reheating, so which is of the order of 10 to the 8 GeV for a frequency of 1 Hertz, and these factors are typically so they are of order unity. Now, nevertheless, so what one gets out of this combining these factors, that the spectrum, of course, as is well known, the spectrum of gravitational waves from inflation is expected, at least in this model, where everything is quite flat, no spikes and so predicted, because it's a single field model with no spikes at all. So the spectrum of gravitational waves from inflation expected is almost flat, up to dips and steps at frequencies corresponding to temperatures at which the equation of states changes considerably. And in this model, of course, we can calculate this equation of state parameters quite exactly, or we can take for the QCD case, so to say in the region where the QCD where the horizon crossing frequency corresponds to the QCD crossover. One has to use results from a lattice on the equation of state, but so it's really remarkable. So if in the far future, it would be possible to measure this spectrum of gravitational waves from inflation. It has imprinted the whole story, the whole so to say the cosmic history in its shape. So one really sees everything from photon last scattering, matter radiation equality, E plus E minus annihilation, neutrino decoupling, QCD crossover, electron-weak crossover. Of course, you have to look in with magnification glasses here, axion decoupling, and the Pecek-Wayne phase transition. Now, of course, unfortunately, there are no. So now we are looking in a bigger perspective. So at least at the level of the that one sees directly this flux. This could be done directly by the future spaceborne interferometer like DeSigo, BBO or so. So what here we took some benchmark values of the parameters here. This for benchmark value, which gives the highest possible thing compatible with the with the upper limit on the tensor to scalar ratio, and this gives the lowest limit in the model predicted in this model for xi equal to 1, and so. And now, of course, unfortunately, so here you could see the QCD phase transition. So of course, this is still too far away from any observability, unfortunately. But here, I think this it should give a strong motivation to look into this region. So if of course a non-zero R is measured in the next stage of CMB polarization experiments, because now if you now would look with a magnification glass in this region, and you really would reach the ultimate DeSigo sensitivity, then you could really measure here in the gravitational wave spectrum. You could measure. So to say the step in the primordial spectrum, which is due to the Pecek-Wayne phase transition. So because as I remembered, to remember, so there are these dips. They are the predicted dips, and this is a predicted dip for a case, for example, of the benchmark point with 0.01 R. Tensor to scalar ratio, and this is the equation of state near the step which you have near the phase transition. Of course, the exact value where this critical temperature depends not only on this parameter lambda, on this Phelps coupling to the 1/4, but it depends also on the Pecek-Wayne breaking scale. We have taken here a Pecek-Wayne breaking scale of the order of 1.2 times 10 to the 11 GeV. This is still quite uncertain. We hope that Marco or Giovanni are giving us numbers for that, because but this is of course until, so it will be the other way around. So I mean, this ultimately SIGO will be in the far future, and until that we should already know the dark matter mass. So if this model is right, then the axial dark matter will be discovered with MadMax much earlier, I think. So, but then this would give a great cross check, and with this you could measure also the self-coupling, so to say. And we will see more things where you could measure this self-coupling. So this gives the bigger picture of this now of the gravitational waves from the inflationary things. So I have plotted this up to very high frequencies, just to emphasize, of course, at some point. So this goes down because there are modes. These are above these frequencies. These modes have never exited the horizon during inflation. Huh? What? Yeah. I mean, this is Higgs, like Higgs inflation. 10 to the 13 GeV. This was this curve. I mean, you cannot. Yeah, it does depend on the parameter, of course, but in this parameter, so you have seen. I've shown. So this is the prediction. So there is a lower bound on the scale of inflation in this model. This is like in Higgs inflation, but it's
a specific value of a Hubble inflation, or because it will all depend on the Hubble inflation.
No, this is the fit to the data gives this curve for the Hubble scale of inflation. So it depends only on so to say, it depends on lambda, this lambda sigma divided by psi sigma squared.
Mm-hmm.
So there's and this is.
So, but when you tell me that you will see these gravity waves at the SIGO, you refer to what Hubble during inflation?
It was hard to understand.
Okay,
so maybe you do it.
So when you say that you will see gravity waves for the inflation, you refer to what Hubble during inflation?
No, this is this curve. I mean, so even if I would took psi to infinity, so then I would lie on this curve. So it's like Higgs inflation has also Higgs inflation has a lower
just don't
bound.
remember Higgs inflation. I'm
Higgs,
asking how much is the scale of inflation.
There is no. So if you go here to large psi even, so but from psi equal to 1 to psi equal to 10 to the 4. There is no, so this line is psi equal to infinity. So there is a lower bound on the scale of inflation in this model.
Okay.
And the lower bound, you can really see this. This is really here. So you see, it's 10 to the 13 if you take this, and the arrow bar here comes from the data, so to say. So this, because this model is very much restricted, so to say.
So you're saying that you will see gravity waves from inflation with a Hubble 10 to the 13 GeV at the SIGO.
At CMB here. This is I mean this is so to say what CMB stage 4 can see. Yeah. So maybe they can so if so this is the lowest point which we would allow, or maybe if you allow to go outside the range of validity, then you could also go here to Higgs inflation. But so this is the, yeah, I'm saying, so in this model this is predicted. So there must be so there is a lower bound, and if this is not seen, then this model is falsified. I like models which can be falsified. So, but of course, still, so even so, as I said, still, so this corresponds to this lower line. This is this lower bound. This is still far away from the things which are presently under the strong debate. So these are the SIGO and BBO. These are more far away projects, so to say. So unfortunately, but we will know much before from these from the CMB polarization experiments whether they see an R. Yeah. So okay. So then, this is now a part of the complete spectrum which we have determined. And let us go to the next part: gravitational waves from the inflaton fragmentation. Now, these are gravitational waves produced in the process of reheating after inflation. Now, inflation will end when rho gets of the order of when rho is of the order of the Planck scale, and then preheating starts. So you have the oscillations now effectively in a quartic potential, because you start at very large values and you don't see the Higgs vacuum or the Pechek-Wien vacuum down at the beginning. And in this preheating process, in these oscillations, you get a violent decay of the inflaton and the copious production of bosonic fields coupled to it. So here we did already at these times we did lattice simulation of the preheating phase, and these are spatially averaged values of the fields of the fields of the inflaton field, so to say, of the zero mode in the direction of the inflaton. And here this other perpendicular direction, or the imaginary part, so to say, of the inflaton. So you get exponentially rapid growth of small inhomogeneities emerging from vacuum fluctuations, and then later there starts the nonlinear regime. This growth will be stopped by violent back reaction and rescattering of waves. And in this phase, one expects inflaton fragmentation, the nonlinear formation and collision of bubble-like large value field regions. So this is from a simulation of Frolov in a simpler model, which shows, so to say, that there are bubbles in the this is now in the energy density in the fields. There are bubbles in the fields surrounded by filaments where or by walls where most of the energy is concentrated, and the collision of such bubbles generate gravitational waves. Now we have done lattice simulations for this model now for SMASH, so the results from them will be published soon. So they are now ready. What here as an illustration, I showed the power spectra obtained by lattice simulations from the theory. Now this is the power spectrum in the direction of the inflaton field. So the real part of sigma. So and what one sees here is that the lowest line for the lowest line are for earliest times, and then the time is increasing. So to say, these are always from time slimes, and one sees how more and more power is, so to say, of course, in this case, for the inflaton itself, had the power was completely dominated in the zero mode, but then how power is coming into higher modes and higher modes, and for the imaginary part, one sees it even more in the imaginary part. In this direction, there was initially no excitation, and this excitation have been growing through in this oscillator or in this preheating phase, and then one sees these resonant pattern that at some frequencies, a lot of power is accumulating in the fields. And of course, this is, so if you translate this now into a three-dimensional picture, then this corresponds to this bubbly phase where there's and it's some direction. So there is really quite a dynamics going on. So and this is now the predicted gravitational wave spectrum, how it emerges, so to say, during this preheating phase in this model. So so there are some features like bumps which come from parametric resonance enhancements at certain frequencies. One can understand that. And but I don't have time to go too much into detail into that. So I have put it here now on the bigger picture. So this is now again this h square omega in gravitational waves versus frequency, and one sees that. So what we could simulate is only the so to say the ranges of frequencies where the peak is. So we have to extrapolate, but there are so one can show that we have started to see this low frequency tail, which should go like f to the cubed. So I think these extrapolations, they are very fine. And here one sees that one gets the maximum of the order of 10 to the minus 10 in this energy budget at frequencies around 10 to the 8 or frequency between 10 to the 8 and 10 to the 9 hertz. So this is, again, these are two curves for different benchmarks. Now, finally, so this was the second contribution, which is much higher than the inflationary contribution, but of course at quite high, very high frequencies. Now, finally, I come to the gravitational waves from thermal fluctuations after reheating. So the nice thing about SMASH is that one can also calculate one can follow the whole theory up to reheating and calculate the reheating temperature and determine it because nearly all couplings are either known or very much constrained from stability and other requirements. So therefore, one can. So we have established that what the reheating temperature is, so to say, in this model, depending on this Xi parameter. And so we know now the maximum temperature of the radiation dominated phase, and from that we can calculate the so-called cosmic gravitational microwave background. So this is the microwave background generated. Yeah. This is here. This is the maximum temperature in the radiation dominated phase. This is the temperature of the. So we have determined it. So as soon as the thermal. So here are the so to say the energy densities. This is the energy density in the background field, and this is the energy density in the matter field, so to say, from the standard model and all these things.
The temperature when radiation starts to dominate.
Yes.
But it's not the maximum temperature.
No, it's not the maximum, but it's where this is the one which we have to consider here. Yeah. So it's I think one could determine it also from this curve, but I have to think of it. Yeah. So and now here.
Sorry about the reheating temperature.
Yeah.
So it means that you follow things until thermalization.
Yeah.
Because you know all the couplings and so on. Because usually that's very hard. Usually people.
It's very hard. So we did Boltzmann equations and all these things. So it was a.
Okay.
The thing is, this is the reason why this paper had 100 pages. because we had to do all these things, and maybe there is still, so it would be good if somebody else would also
And just to be sure, because
do
that's
it
also
again.
one of my questions.
Yeah.
Usually the fact that you're able to say, okay, this transition happened at this precise frequency, or Hubble exit of the CMB scale was at that number of E-fold during inflation, is precisely because you were able to track the whole expansion history throughout the universe. Otherwise,
Yes,
there is
because we could also show, so to say, because this is essentially reheating. So we could show that the transition from inflation to the so to say to the preheating goes very fast, and one immediately goes from a vacuum energy dominated phase into a radiation into a phase which has W equal to one third.
But this is a bit.
It's a pre-thermalized, but this is the reason for that is you have a conformal. So the potential is quartic, so to say, for these oscillations. So this has no dimension. This is for example, in Higgs inflation, you come from inflation to a matter-dominated like expansion, and later to a radiation-dominated expansion. And here so there is no, and therefore you can make this transition very, very precise, because it goes. I don't have the picture here, but we have also determined, so to say, this curve. Yeah.
Thanks very much.
Yeah. So what we did here, so this is the formula which you get for the cosmic gravitational microwave background. So now so there are a lot of well-known things and about the temperature dependence and the dependence on these factors. They come all from the evolution, so to say, between the generation and us. But this factor is essentially the source term for that, and this is at large wavelengths. This function, so to say, where this is essentially k over t, but now it's the k today, so to say, the frequency of today over t0 corresponds. So the advanced large wavelengths, or at small argument here. So the CGMB is sourced by macroscopic hydrodynamic fluctuations and described by the shear viscosity of the plasma. But at small wavelengths corresponding to large wave numbers, it is sourced by particle collisions. And the corresponding source term is then suppressed by the gauge couplings and Boltzmann factor. And fortunately, so this is now known to complete leading order for generic weakly interacting BSM extension with gauge fields, fermions, and scalars due to the calculations of Cilieri and Leine and collaborators. And we have generalized all this to an arbitrary BSM extension in order that we can do this calculation also for example, for SMASH. Now so the source term looks like that. So it's k to the third time k over t to the third times this source term. Now for the standard model, it's very weakly depending on the temperature, because it's only it depends as expected. It depends only on the gauge coupling, so to say, squared, and because of asymptotic freedom. This runs only logarithmically, but you see this looks very much like a thermal, like this Boltzmann term, so if you now fold this in and calculate that. No, it's like, so for example, you can think of Bremsstrahlung. And you can the thing, the dominant one are if you have to exchange the gauge boson of the standard model. So it's a dominant T channel process. For example, you could have a photon and an electron goes into goes in a graviton and an electron. So it's like such Bremsstrahlung processes. And but of course, now you have to do this with hard thermal loop and all these kind of things. But so I think I don't have the diagrams with me, but it's yeah. So these three level diagrams in a sense. And now you see, so this is the dip, or this is the dip from the thermal, so to say, from the beginning of the hot Big Bang after inflation and after reheating. So it still sticks out from the reheating, but it's of course it's orders of magnitude below. So the height of this dip goes linearly with the maximum temperature or with the reheating temperature. How should I call it? So what would you like better, the maximum temperature of the hot phase or the reheating temperature? So it goes linearly with this reheating temperature. So and you see, so there is a, yeah, because it's only 10 to the 10. So in Higgs inflation, they claim that the reheating temperature can be 10 to the 14. So this peak would be higher. Now, so what are the observational prospects to measure this complete spectrum? So so here now I have what I'm plotting here is now, instead of this h square omega, I plot here the characteristic dimensionless amplitude of stochastic gravitational waves. And here is the prediction from SMASH. And here are the present limits which are available in this high frequency region. So for example, of course, here there is the dark radiation limit, which applies for this thing, because this is a very broad distribution. And if you can integrate all this together and compare it with the number of effective degrees of freedom seen at low energies. And so this is a dark radiation current. So at the moment, so there's no problem with that. So there is not too much gravitational waves predicted by the theory. So unfortunately, the present limits, they are very far away. So from the Fermi polometer, from haloscopes with ALPS, we have also established a limit on gravitational waves, but it's at 2 to 10 to the 14 hertz, and so on. So these experiments, they work with the principle of conversion with the so-called inverse Gerstenstein effect, conversion of gravitational waves in strong magnetic fields into electromagnetic waves. Now, and this is somehow, you see, this is somehow the prospected sensitivities on the characteristic amplitude of stochastic gravitational waves. So I see, so of course, so we see that at low frequencies where the interferometers are planned, so there is some hope that at one day one can go there. At higher frequencies, at present, so it seems still we are still far away from the predicted sensitivity, and on the experimental ground, one has to do a lot in order to probe really the early universe, like preheating, the preheating, and so to say the start of the hot Big Bang, which would be here. Now, my summary. So I've presented the state-of-the-art predictions for the complete spectrum of the primordial stochastic gravitational waves in a well-motivated and highly predictive minimal model of particle physics. This can be seen, I would see it as a conservative benchmark for the expected gravitational waves from the early universe. Of course, would be spectacular if there are cosmic strings or phase transitions and all these things. But so this is somehow, this is a quite conservative model, which fits to our today all the data and gives right and explains everything what we want, so to say. And it's so simple, but the gravitational wave spectrum, at least it's there. There are minimum. There are, so to say, there are guarantees that it cannot be smaller. So at least in this model. However, of course, it's still far away. But I see it as a conservative benchmark for the expected gravitational waves from the early universe. And we theorists, we should also be so not only produce exciting things and say, oh, what can we all test all and so on, but sometimes also to step back and say, so what is the minimum we could expect, and then the experimentalists could also say maybe we should not give up. So if we didn't see these spectacular things which they have all predicted, so like at LHC we have predicted supersymmetry and so on, there is no supersymmetry. Now here, if you predict here all kinds of cosmic strings and so on, so that's that. Of course, we should do that, but we should also have, so to say, step back sometimes and say, okay, what is the minimum which we expect, and then the experimenter can say, okay, what do we have to do in order to reach this minimum? So just to have this in mind. Of course, it would be better that we see spectacular things now in the next 5 or 10 years. So I think this gives the strong motivation for future space-borne gravitational wave interferometers such as Ultimate DeSigo, and for the development of new gravitational wave detectors sensitive at the megahertz to gigahertz frequencies. Currently, a community is forming which seriously considers the search for ultra-high frequency gravitational waves, and Raffaele was also participating in our events and so on. So there was also in the last month there was this ultra-high frequency gravitational wave workshop. A theory and technology roadmap is in planning, so to say, and I think revealing the cosmic history sets an ambitious but rewarding goal for this kind of enterprise. Thank you very much.
Questions? There.
So very quickly, the first one is about, so let's say that we do detect.
You should, it's really hard.
So let's say that we do detect primordial gravitational waves, say at CMB scales, light burn. So first of all, we all celebrate. And then the second bit is, can you tell that it's smash and not say Starobinsky inflation or?
I can only tell it, what I'm saying, I can only tell that it's smash if I see also the Redshift-Quinn phase transition in this primordial spectrum. But but this is a prediction of this theory. So as I said, the prediction of smash is that there is a break at around 1 hertz. So this is a strong prediction of that. So, and from that, so of course, I think, and this is only an example, as you said, of course, these oscillatory or all kinds of features, they are more spectacular, but it could be also that, so if you can measure this primordial spectrum, it would be even better if it's really flat everywhere, and then you can see, so to say, the equation of state changing of the universe. That would be marvelous. Yeah, I mean, you see it all imprinted on a spectrum, which you should possibly be able to calculate precisely. And
okay, and the other question I have is, as far as inflation goes, it seems your prediction is entirely constricted, right? You're not fixing anything. The model gives you that.
yeah,
When it comes to reheating late, are
Yeah.
you assuming anything that I'm not aware of, or there's no assumption at all?
no, we are really using the equations of motion of this theory. But so what we do in the reheating is you are really doing lattice simulations, so to say, of the scalar sector and also of the Higgs. So taking into account also the Higgs decays, standard model radiation, and impact on scale factor evolution. All these things are taken into account, and we are doing it. So I mean, if you do it for another, so the result of the reheating will always be model dependent. So we can only do this in this model. So now,
for this model,
I think we have done as far. So at the moment, I cannot say about the error bar. Yeah, so that would be nice to know the error bar. But for this model, so at least what we did is we can so to say we have all the kind of input parameters. We put them in, and then we do the simulation. So it was with a big lattice, and so to say for one run, it was running for 7 days, and we computed it for very long times, because all the other simulations before, they have been for shorter times and so on. But of course now, so I would like, for example, to do it also now for Higgs inflation, but not for the version which is of the old version, but one which is at least perturbative. Okay, but this is one which has also an R² term. So, but this could be done, I think. So and then one has another benchmark and so on. But of course, I mean, these things, and so this. And this is a model. So there are other models with reheating, which are other kinds of inflation, yeah, which give then other kind of reheating probably. So I mean, it's so the reheating part is model dependent. So if somebody tells me what the maximum temperature was after inflation, so this curve is very generic, yeah, for all single field models. And this term is also very generic for all the models. We should just know the temperature, so to say, of the maximum temperature of the universe in the phase, and this gives the tip. But this thing is model dependent.
Thank you.
But this was so for SMASH, it was also very. So we were really surprised at the time. What came out in SMASH is, for example, this was very restrictive. Also, then for the phenomenology was that from preheating, you get that automatically the Peccei wind symmetry is restored already non-perturbatively in the, so to say, in the first round of preheating, and therefore you are automatically driven in the post-inflationary scenario, and then you get a lower bound on the axion mass and all these things. And so I found this good for this model, that it restricts so much. Yeah, Pasquale.
Just about being optimistic.
Yeah.
Maybe I missed it, but don't you expect also additional signatures from topological defects coming from your axion sector here?
They are, I mean, they are, but so you don't get this from this cosmic, the cosmic strings associated with that. They don't give you enough. So I mean, you have to, not for the axion, you have to have an axion-like particle. So Marco did this.
No, I was not talking about gravitational waves, but you do have signature associated to. I mean,
yeah. It is the dark matter abundance.
There are even issues associated to isentropic modes and so on. So,
but this is the post-inflation. This has automatically a post-inflation.
I mean,
yeah.
I should go back to the slide where the scale where.
No, but this model is, so to say, there is the so to say, the Peccei wind symmetry is broken after inflation. And so
you should have topological, you should have strings.
Yeah, and this is what they have to determine. These strings, they disappear, so to say. They are not. I
don't know what to say, but the strings disappear at acute phase transition if you have one domain wall. Okay, n plus one domain walls. I don't know what you do.
So this was a so-called domain wall number 1 model, which we have here considered. So this has no. So the strings are unstable, so to say. They disappear, and there are no domain walls and nothing. So there is. So in the early universe, of course, they are generated.
Yeah,
So
and
it
then-
means
They
that your-
produce
yeah,
axion dark
it
matter.
means that your prediction of the dark matter abundance will be crucially dependent on that. then.
Of course, and this is was the
It's-
reason. So, maybe I did
how is
not-
it so narrow?
This
I-
was
I'm
the
a-
reason. The reason why I took this reach. Where is it? Why I took this. So this the Patrick wind scale is restricted to this range because, of course, we want to have that 100% of the dark matter is axions. Now so if the dark matter
Okay.
abundance will fix in this model the Patrick wind
Okay.
scale, but at the moment there are these big uncertainties from the
So
simulation.
just for me to understand, because probably I
Yeah.
completely that in all of your parameter space,
Yeah.
the dark matter comes from string decay. There is no misalignment relevant production here.
There's a prediction. I mean, if you go here to the upper end of this
Yeah.
of this thing, then you have no. So this is the upper end. So then this corresponds to 28 microelectron volt. So there is no contribution from the strings, and here at the lower end, 100% contribution from the strings. And so this is and this is at the moment we don't know, so to say, what is the partition. Or you can.
No, yeah. So the bound, okay, the bound we give is the FA, which is that V sigma smaller or equal to 10 to 10 GV. If okay, coming from string decay, then the answer coming from extrapolation and the fact that we don't know what is the abundance coming from the main walls. That's so essentially there's an upper bound on the value of FA, which is that V sigma in this scenario from that matter of production.
So the problem is, so when we wrote this mesh paper, we were more optimistic. We had we were saying that it had a smaller range of V sigma, but this was also just based on the simulations of that time. And now we have to, so this is open, so to say, and there are still, I think there are still different results from different groups, and so this is a very active field, so to say. Yeah.
Okay, can I ask something related? So you take T maximum of 10 to the 10, but then you have for example FA 10 to the 11, and I would guess that in that case you.
But you have here the Patrick wind.
No, but the phase transition is not happening.
Is at lambda to the 1/4 of V sigma. And this
also-
lambda is 10. Lambda to the 1/4 is 10 to the -2. So
Okay.
yeah, so this
Okay,
is.
so you.
This is, I mean, here is the, so this was determined by Daisy resummation and all these things, but we have several restrictions on these couplings due to stability and so on. And then all this boils down to this rather simple.
So after inflation, you restore this species
after, so it is,
thermal effect.
when we have this kind of inflaton, so this mixed inflaton, then really, then we also thermally restore the Patrick wind symmetry. In the other, when we have this other direction, then all the just along the Patrick wind field, then there are effects which block, so to say, the efficient thermalization. And then we get the problem with dark radiation, so to say, from axions and so on. So or we don't know. So it's borderline. So, and we didn't want to look into this more.
Okay, thank you.
Yeah.
In your plot with the contributions to the gravitational wave spectrum,
Yeah.
the contribution from stops abruptly at, in your example, 8 hertz. I don't understand why it would stop at a value which is even smaller than the values excited by reheating. Is it because
so,
they are?
I mean, it's
Yeah.
so there have been investigations. So we see it already how it goes down. So we didn't follow. So we wrote it down. But there are recent works which consider this more in detail. So it will not be a complete. Abrupt stop. So this is where we have shown the lines. So this is up to which we have calculated. So I mean,
Okay,
that-
okay.
And
It
we
could
said, okay,
extend a
we
bit,
don't
yeah.
care. This is so much
Mhm,
about.
okay.
Yeah, but that's true. Yeah.
Yeah, because if you can enhance perturbation by another mechanism at 10 to the 11
Yeah.
or 12, then probably inflation can also go until there, but maybe.
Yeah,
with a
that's true. One should,
through- yeah, okay.
what we should, so this is which just came out of our calculation, and the rest we just said, okay, no, forget it. But maybe we should have stopped here.
Are there any more questions? Not, let's thank Andreas.
Yeah. And I think we should thank the organizers and all for the hospitality and for everything. Was really great. Thank you for being so brave.
Thank you very much. And yeah, with the occasion, I wanted to thank the speakers and all of you for coming this week. So I will see some of you next week, but I'm leaving soon. So goodbye to everyone else. And I'm looking forward to meeting all of you soon somewhere else. Hopefully equally nice. I mean, I think we all enjoyed Florence. Goodbye.